Module 4 built powerful estimators, but every one of them rests on a promise you cannot check. Given the things you measured, treatment is as good as random. And every diagnostic you ran, balance tables, overlap plots, weight checks, only inspects the columns that exist in your data. The referee's killer question is the one none of them answer. What about the confounder you didn't measure? Two bad replies are common. 1. We adjusted for 47 variables as if quantity were proof. 2. Observational data can never prove causation. Pure despair. The honest move sits between them, and it is the name of this module: judgment. Stop asking whether an unmeasured confounder exists, it does, and start asking how strong it would have to be to overturn your result. Here is how you turn that into a number. For a hidden confounder to fake your effect, it needs 2 arrows. One into treatment, one into the outcome, both beyond what you already measured. And the bias it can produce is capped by the weaker of those 2 arrows. So you can compute the minimum joint strength any such ghost would need to fully explain your result away. That minimum is the E-value. Take Module 4's answer, risk ratio 1/2. Flip it to 2 and the formula gives 3.41. Read it as a sentence. An unmeasured confounder would have to be tied to both starting a statin and having a heart attack by a risk ratio of 3.4, each beyond everything you measured, to erase the effect. Picture it. Any confounder is a point on this plane, and only points in the shaded region can explain the result away. Now calibrate. Your strongest measured confounder, LDL itself, sits around 2. Claiming an invisible variable nearly twice as strong is a claim that needs defending. The E-value interrogates a hypothetical ghost. A negative control goes hunting for real ones. The trick: find a question whose true answer you already know is no effect, but which carries the same confounding as your real question. Run your exact pipeline on it. If it finds an effect where none can exist, you have caught your bias red-handed. The famous case, observational studies kept finding that flu vaccine halved death in the elderly. Then someone checked, and the protective effect was just as strong before flu season even started. When the vaccine could not possibly work, the pipeline was detecting healthy vaccine bias, not immunology. Draw it as a graph. The unmeasured confounder points at everything, but a statin cannot biologically cause, say, an accidental injury. So any statin injury association can only have traveled through the confounder, which makes injury an alarm bell for failed exchangeability. The E-value and negative controls handle the ghost. Quantitative bias analysis handles the imperfections you can actually measure. Remember Lesson 9's ledger. Heart attack was really a billing code with a known accuracy, a positive predictive value, and a sensitivity from a validation study. Those are not hypothetical, they are numbers. So plug them into a bias formula and recompute the estimate without the error. One useful instinct: if the miscoding is the same in both arms, it usually just dilutes your effect toward no effect. So your risk ratio of 1/2 is, if anything, conservative. The dangerous kind is differential, when treated patients, seen more often, get more chances to have events recorded. That can bias either direction, which is exactly why the ledger preferred outcomes you cannot miss, like death. Put it all in one picture, and you have what a defended estimate looks like. The primary result, risk ratio 1/2. Around it, the analyses that tried to kill it. Require a second prescription fill, still 1/2. Correct for the outcome, miscoding, still about 1/2. And the negative control, accidental injury, lands at 0.97, spanning no effect, it passes. Across the bottom, the E-values, 3.4 for the estimate, 2.1 for the confidence limit, benchmarked against measured LDL near 2. The results section stops being a single number defended by adjectives and becomes a number surrounded by the attacks it survived. That is the difference between an emulation and an anecdote. So every assumption Module 4 leaned on now has a named probe. Exchangeability fails through an unmeasured confounder. Probe it with E-values and negative controls. Positivity fails through extreme weights. Probe it with overlap plots and truncation. The outcome is mismeasured. Correct it with bias analysis. Censoring is informative. Vary the censoring model. A defended estimate is not one that assumed nothing. It is one that named its assumptions and tried to break them in public. Next lesson, Capstone A. A published emulation goes on the table and you grade it. Protocol component by component, defense by defense. See you in lesson 15.